Condenser and cooling tower. Condenser is a closed heat exchanger in which steam coming out of turbine is condensed by cooling tower and vacuum is maintained, resulting in an increase in work done and efficiency of steam power plant. Help to restore or recover feed water back to boiler. Advantages: increase work done and efficiency due to lower pressure of condenser, help to restore high quality feed water back to boiler, decreases steam consumption rate ms dot for the same power output due to increased work done, reduces thermal stresses due to high temperature of feed water entering to boiler, cost saving as only makeup water is to be treated instead of full water. Important points: out of total heat supplied in the boiler, uh, only up to 60% is rejected in the condenser. In open system, cooling water requirement is approximately 50 times more than steam flow rate ms. Even with closed system using cooling towers, cooling water required is about 5 to 8 kg per kilowatt hour for 2000 megawatt, 24 into 10 power 4 tons of water per day. 5% evaporates in cooling tower. Make up cooling water per day 12 into 10 cube tons per day. Cooling water takes latent heat of steam, so temperature of water may increase up to 10 degrees. Types of condensers: direct contact cooling tower is directly mixed with steam to make a single steam. Here both mass as well as energy interaction takes place. Surface condensers, indirect type. These are proper heat exchangers where there is no mixing of cooling water and steam, only energy transfer takes place. Direct type: spray condenser, barometric condenser, jet condenser. Spray condenser, feed water for dry cooling tower, fan heat rejected, then goes to turbine exhaust condensate, air removed by air ejector. Heat balance: H2 M2 dot plus M5 dot H5 is equal to M3 dot H3, but M3 dot is equal to M2 dot plus M5 dot. So M2 dot H2 plus M5 dot H5 is equal to M2 dot plus H3 plus M5 dot H3. So finally M5 by M2 is equal to H2 minus H3 by H3 minus H5. Important points: M5 greater than M2 as latent heat, H2 minus H3 greater than sensible heat, H3 minus H5. Cooling tower is mixed with steam at equal pressure in condenser. Drawback is high requirement of high quality cooling water, DM water. Barometric condenser: cooling water is made to fall in a series of baffles to expose large surface area for steam feed from below to come in direct contact. Condensation of steam takes place and mixture falls to hot well through tailpipe. A higher height of tailpipe will increase the pressure of condensate from below atmospheric pressure to atmospheric pressure of hot well. P atmospheric is equal to P condensation plus rho GH minus delta PF. Delta PF loss due to friction. If delta PF almost equal to 0, H is equal to P atmosphere minus P rho PC by rho G, which is equal to 9.57 meters. P atmosphere is equal to 101.325 kilopascal. PC 7.4 kilopascal for 40 degrees centigrade temperature. Rho G is equal to 9810. So height of tailpipe required may be from G to from 9 to 10 meter, which result in very tall structures, so not preferred. Delta PF directly proportional to height of tailpipe, and to minimize delta PF we should increase diameter of tailpipe, and which makes bulky, so not preferred. A jet condenser baffles are replaced by cascade and a cascade to increase surface area and to decrease the height of tailpipe. Diffuser is provided. Cascade turbine to boiler from VFP, jet turbine exhaust, cooling water, cooling tower, hot oil. More compact compound of barometric type diffuser help to increase pressure in a short distance. Direct contact not preferred as large amount of water DM required and purity of water also decreases. Surface or indirect condenser. Almost all thermal power plant used these type of condensers and are simply shell and tube heat exchangers. Design steam from turbine start MC TC1 TC2. Steam condensing TC1 TC2 cooling water TTD. Logarithmic mean temperature difference LMTD delta Tm is equal to delta Ta minus delta Ta by ln delta Te by delta Tc. Delta T is equal to Tsat minus Tc1, delta T is equal to Tsat minus Tc2. The rate of heat transfer from condensing vapor to cooling water is Q is equal to Ms into H steam minus H condensation is equal to MC Cpw into Tc2 minus Tc1 is equal to UO AO into delta Tm is equal to Q, where UO is overall condenser heat transfer coefficient based on outside tube, AO is total outside surface area, delta Tm is LMTD, AO is equal to Ms into HT minus H condenser by UO, delta Tm is equal to N pi DOL, N is equal to number of tubes, L is equal to length of one tube, single pass, DO is equal to outer diameter, MC is equal to N into pi by 4 di square into rho W VW, rho W is equal to density of water 10 cube kg per meter cube. VW is equal to velocity of water 1.8 to 2.5 meter per second. Okay. Normally N 50,000 on high side, water diameter 22 to 25 mm. Pumping power required P is equal to MC into small v delta P is equal to MC delta P by rho. Delta P pressure head to be developed by pump to overcome losses. Pressure losses mainly due to pressure drop in water box. Pressure drop due to friction in tubes directly proportional to FLV square by 2D into rho. Surface condenser 2 pass more preferred. Single pass better overall efficiency but consume more power. 2 pass turbine exhaust support plates support by undivided water box shell tube water sent in water out divided water box. Mode of heat transfer is by convection. Tube length is from 9 to 15 meter. Such long length of tube result in large rise in temperature of cooling water and thus condensing ability decreases at exit ends of tube. Therefore, tubes are kept closer to the cold end compared to hot end. Cold and hot end. An expansion joint allow for different rate of expansion between tubes and shell. Tube materials of condenser has to withstand the temperature difference, pressure differential, and load, so that tube material may be cupro nickel, aluminum, brass, aluminum, bronze, muntange metal, admirably alloy, stainless steel. Vertical support plates are used to provide support to long tubes and to prevent tube vibrations. Single pass condenser with the same total number of and size of tubes, that is the heat transfer area, and with the same water velocity required twice the water flow but results in half of water temperature range and thus lower condenser pressure. Single pass is good for plant thermal efficiency and reduce thermal pollution but require more than twice the water and hence 4 times pumping power. Two pass is more common in power plant. Circulating water system once the closed loop. Once the used where a large source of water available, water taken from a reservoir used and discharged back to reservoir more efficient, cause thermal pollution. Closed loop warm water from condenser is cooled by some device like cooling tower and recirculator loss due to evaporation require makeup water, reduces cooling water demand. Cooling tower cools the hot water from the exit of condenser and feed back the cooled water back to condenser. Cooling tower at type right type. Basics of psychrometry. P atmosphere is equal to PA plus PW. PA partial pressure of air. PW partial pressure of water vapor. TS PS PW DBT WBT DPT. At 15 degrees, PW is equal to 1.705 kilopascal, PA is equal to 99.62 kilopascal, P atmosphere 101.325 kilopascal. As PW is very less, water vapor in air exists in superheated state and air is said to be unsaturated. Saturated air holds the maximum water vapor at given temperature. If temperature increases, it can accept more water vapor till it again becomes saturated. If temperature decreases, some water vapor will condense and the new cooler should be saturated. Some terms, specific humidity or humidity ratio W. The ratio of mass of water vapor per unit mass of dry air, W is equal to mv by ma is equal to kg of vapor by kg of dry air. Now as PV into V is equal to mvrvt, PA into V is equal to marat, PMV by ma is equal to PV by PA into RA by RV is equal to PV by P minus PV into 8.314 by 28.96 into 8 by 8.314 by 18. W is equal to mv by ma is equal to 0.622 into PV by P minus PV. Relative humidity or humidity ratio, pi ratio of partial pressure of water vapor in air to saturation pressure, P set at air temperature, pi is equal to PV by PS. TS degree of saturation mu is equal to the actual specific humidity by saturated specific humidity is equal to W by Ws. Dew point temperature dpt, when air is cooled at constant pressure, the temperature at which water vapor starts condensing is called dpt, dew point temperature. Dry bulb temperature, temperature recorded by thermometer with a dry is called dry bulb with a dry bulb. WVT, wet bulb temperature, temperature recorded by a thermometer within the bulb is covered by cotton saturated with water. Note, in if air is saturated, pi is equal to 100%, WBT is equal to dBT. Normally dBT greater than WBT greater than dPT. Efficient enthalpy of moisture, H is equal to H air plus H vapor is equal to MA CPA plus MV into HG plus CPV into T minus TS. CPV is equal to 1.88, dividing both sides by MA. H is small h is equal to CPA plus W into HG plus 1.88 into T minus TS, where MA by MA is equal to W. Cooling tower. Cooling towers. Wet cooling tower have a hot water distribution system that showers or spray water from horizontal bar known as fill or packing. The water flow downward through packing in the form of splash and mixed with air directly from atmosphere that enters from bottom and flows upward due to drought, which may be forced, induced, or natural. Air entering tower in is saturated is unsaturated, and as it comes in contact with water, spray water continues to evaporate till air becomes saturated. So minimum temperature to which water can be cooled is adiabatic saturation or wet bulb temperature of atmospheric air. A cooling tower is specified by approach A. Difference between exit temperature of cooling tower and wet bulb temperature of ambient air. A is equal to Tc2 minus Twb2, which is 6 to 8 degrees. It is unattainable temperature difference. Range R, difference between inlet and exit temperature of cooling tower, R is equal to Tc1 minus Tc2, which is 6 to 10 degrees. Cooling efficiency, ratio of actual cooling water to maximum cooling possible. Eta cooling is equal to Tc1 minus Tc2 by Tc1 minus Twbt. Wet cooling tower have two type of drought mechanical, natural. Induced, forced. Mechanical rot air is moved by one or more fans driven by motors, preferred for low approach and broad range. Induced rot mostly is the ID fan at top of tower, so it maintains the tower at negative pressure, thereby reducing leakage. Most widely used. Fan forced rot less preferred. FD fan is mounted on lower side of tower since it operates on cooler air. It consumes less power. Disadvantages: air distribution problem is in fill causing channeling, leakage of air, recirculation of hot and moist air back to tower. Advantages of mechanical rot: low investment construction, assured supply of the required quantity of air at all load and climatic conditions, small physical structure. Natural drought: flow of air occurs due to natural pressure head created due to different density difference between cold outside air and hot humid air inside. Pressure head developed if delta P is equal to rho O minus rho I into GH, whereas rho O minus rho I is very less, height H required is very high, so natural drought cooling towers are very tall. They are made mostly of hyperbolic profile, as it offer superior strength and best resistance to outside wind loading. Initial cost is very high and require more space. Natural drought is preferred. In cool, humid climate, low WBT and high relative humidity pi. When WBT is low and high condenser water inlet and outlet temperature, broad range and long approach. In heavy winter loads, losses in wet cooling tower, evaporation 1 to 1.5% water, drift, fine water droplets carried by air 0.03%, baffles decrease drift loss, blow down water lost out during eliminating dissolved solid contents 1 to 1.5%. Makeup water 2 to 2.5% is added to compensate these losses. Dry cooling tower used where water is not surplus, even to compensate for makeup water. In towers, warm water from condenser flows through fine tubes over the cooling air is passed. Heat is rejected to air as water is cooled. Steam from turbine, steam heater, aero, FD fan, direct dry cooling. Here, turbine exhaust steam is admitted to a steam header through large ducts to minimize pressure drop and is condensed as it flows downward through a large number of finned tubes or coils arranged in parallel, which are cooled by atmospheric air flowing through natural or forced draught. Indirect dry cooling tower, surface condenser, hot air, cold water, hot water, air. It uses conventional surface condenser in which circulating water leaving the condenser goes through finite tubing cooled by atmospheric air in tower. Heat balance in cooling tower, MW MW to TW to cold water MA plus MV, cold air W1 MV1 by MA, hot water MW1 TW1, inlet hot air outlet MT2 MA plus MV2. Makeup water is equal to MV2 minus MV1 is equal to MA into W2 minus W1 is equal to MW1 minus MW2 is S by S of A. E in is equal to E out MA into CPA T1 plus W1 into HG plus 1.88 into T1 minus T set plus MW1 CPW TW1 is equal to MA dot into CPA into T2 plus W2 into HG plus 1.88 into T2 minus T set 2 plus 1 W2 into CPW TW2. Air ejector, it is important to remove non-condensable gases that gets accumulated in condenser. The non-condensables are mostly air that leaks through joints into condenser due to negative pressure gradient. It also includes gases due to decomposition of water into oxygen and hydrogen by thermal action and by chemical reaction between water and materials of construction. These gases affect condenser. As condenser pressure increases, efficiency of cycle decreases. They blanket a heat transfer surface. Heat transfer decreases. A problem of chemical reaction like corrosion. Air ejector working. Condenser motive air stream. Main tube nozzle suction diffuser. It uses main steam at a reduced pressure that enters a driving flow nozzle in the first stage ejector, from which it exits with high velocity and momentum, but at reduced pressure. This reduced pressure draws non-condensable from condenser, as a result of momentum exchange, gases are carried by steam jet. The combined flow of steam and gas is now compressed. P increases in the diffuser of first stage ejector and discharged into steam small intercondenser where steam is condensed. Cooling is here is done by main condensate part of feed water heating system. Heater cycle increases. The more the non-condensable and remaining steam are then passed to the second stage ejector, where they are compressed and passed to an after condenser known as vent condenser. The steam, if any, get condensed. The non-condensables at higher pressure than atmospheric pressure is vented out. Two-stage steam jet ejector. This is two-stage steam jet